Good day, everyone. This is MEM Group 34 with a plug-and-play IoT device for structural health monitoring applications. We're going to jump right into our outline of this presentation, starting with the introduction. Currently, there are three main types of maintenance. Reactive, which is emergency maintenance caused by preventable faults. Planned, which is a scheduled maintenance, regardless of its state. Proactive, which is when an engineer takes the time to survey a structure and bring back that data to be analyzed, finally giving a solution for a state that might appear. What these maintenance procedures have in common is that they are manually collecting and analyzing structural data, the lack of real-time diagnostics of structures, and a lack of detailed historical diagnostics reports to help track issues. We are proposing a new maintenance method, intelligent maintenance. This method will predict the current state, its later state, and how to fix it ahead of time, all in real time. Our device will utilize an IoT approach to current structural health monitoring problems. What is structural health monitoring? Well, this refers to the process of implementing a damage detection and characterization strategy for engineering structures. This strategy makes a diagnosis over time on the state of the materials and the parts that make up the structure. Currently, data is only being collected and transferred to an engineer to be analyzed. This means no real-time analysis is being conducted due to the sheer volume of data. On this project, we have our stakeholders, funded by the Theoretical and Applied Mechanics Group at Drexel, L3 Harris, and Noesis Analytics. The stakeholders have outlined a need for an IoT device which fits in with existing data acquisition networks and performs user-defined real-time analytics on the collected structural health monitoring data. The total budget allocated by our stakeholders for this project is $5,000. They plug-and-play IoT device leveraging fog and cloud computing to provide real-time structural diagnostics and visualization.
On the screen now, we can see an overall architectural framework of our proposed approach. Here, the fog device connects to an existing layer of acquisition systems and serves as a place where all data collected from the environment is aggregated. The aggregated data is then passed through various filters and machine learning models to create a stream of only useful data, which is then transmitted to the cloud in near real time. The machine learning models that run at the fog is trained at the cloud, and only the resulting models is propagated back to the fog device to classify live data. Lastly, as the real-time process stream of data reaches the cloud, we compute and visualize various statistics about the overall health of the connected structures.
Based on our stakeholder needs, we curated a list of target specifications/standards for our project. Let's go through them one by one. We want our device to be compatible with all existing DAC networks. We plan to achieve this by matching the settings of the incoming data with the client's DAC system. We also want our device to analyze data all in real time. To do so, we're leveraging the power of the Jetson, along with high performance input-output speed of the SSD card we provided, and fast internet connection. Lastly, we want our device to be user-friendly. We're achieving this by packaging our device with a user-friendly web interface, which will allow them to interact with the device with ease.
To address our target specifications, we define the system flowchart shown on the screen now. The journey of the data starts in the environment and is picked up using sensors. The sensors used depend on the user and can be chosen from a wide range of options available. For example, acoustic emission, cameras, temperature sensors, etc. The sensors connect to an array of data acquisition systems. These systems can consist of any acquisition instrument that have networking capabilities. From the acquisition array, the sample data is then sent on to a network mapped folder onto the proposed fog device. At the fog device, all incoming data is aggregated and passed through various filters and algorithms. First, if we expect the incoming data to be noisy, the data is run through a layer of user-defined filtering algorithms. Next, since some incoming data such as voltage versus time signals for acoustic emission does not always tell you the full story of what's actually happening in the environment at the moment, the data is passed through a layer of feature extraction scripts. For context, From simple voltage versus time waveforms, we can extract information such as amplitude, rise time, peak frequency, etc. The features to be extracted are decided at the cloud by a Pearson coefficient analysis performed on historical data. Note, this part of the process was only tested offline due to physical and time restrictions created by the COVID-19 crisis. In tests done in the winter quarter, the feature extraction portion was handled by the data acquisition layer. Moving on, the last layer of computation in the fog device consists of running the extracted features through a layer of user-defined algorithms. The purpose of applying machine learning close to the environment is to limit the amount of information sent to the cloud to only the most useful chunks of information and maintain a near real-time data flow. The previously mentioned extracted features are fed into user-defined machine learning models, and only the resulting information is propagated to the cloud in real time. Of course, all data collected from the environment is also sent to the cloud, but this happens at a slower rate since historical data is only used to train the models that actually run real time. At the cloud, all incoming data is received by a MongoDB database server. This MongoDB server can be accessed by networked computers and a dedicated web server node. The network computers are responsible for training all models to be run on the fog device, while the web server hosts a user-friendly web interface. From this interface, users can visualize their data, configure acquisition parameters, pick filters, and also machine learning models. Furthermore, in future iterations, users will also be able to create custom models using an interactive algorithm builder.
On the screen now, we can see our final prototype of the proposed plug-and-play device. The BNP device is based on an NVIDIA Jetson Xavier single-board computer. Other peripherals include one 512GB Samsung 970 Pro SSD card, one AC8265 Intel dual-band wireless chip, one Sierra Wireless MC74554 GLT transceiver module, one LiPo battery, and all accompanying connector and antennas.
Here on this screen, we can see our prototype web interface. After users log in, they will be greeted by an adjustable dashboard that displays the most important information about their structures. Near the top, we have three light signals in green, yellow, and red, signifying pristine, comprised, and critical states of the chosen structure respectively. More detailed analysis results can be seen on the various graphs and charts in the dashboard. Other tabs include data format setting, algorithm and filter selector, and parameter settings. From the data format tab, users can inform the fog device what kind of data to expect from what acquisition system. From the algorithm and filter selection tab, users can select what filters and algorithms to run on the fog device. And from the parametrics settings tabs, users can change acquisition parameters on the remote acquisition system. There, on the next slide, you can see our live demo taken in the winter term that can give it more detailed about how to use this interface.
In this test, we're collecting acoustic emission waves from these picosensors. The waveforms are being collected by this instrument over here, this data acquisition system. It's also extracting the features for us currently, but we're planning on doing that ourselves in our Jetson device later. So what's happening is we're collecting the data from this setup, and this data is being propagated to our fog device. Jetson is right there. Could you show them a shot of the Jetson? So basically what's happening now is data is being collected on this device, it's being aggregated, and we're passing it through various filters and also performing real-time clustering. So since we're only doing a noise test now, we're only going to be seeing one class. So let's start the test. There you go. I'm producing some signals that is being read in by that interface in real time. Pretty much no lag. And now if we go here to our web interface, the data is there as well. The web interface updates once every 10 seconds. updating, and we also have, you can start, stop, select DAC, and basically this is our dashboard. Done.
Let's really get into the details of this device in the discussion section. Starting with our testing setup. On the screen is a MTS machine, a common machine used for applying loads onto specimens. Historically, aluminum samples have been tested on these devices, but our goal for the spring was to use this testing method on a common building material like steel. Towards the middle of the slide, we can notice the location of the piezoelectric sensors. These sensors pick up acoustic emission waves. Now, what are these waves? Piezoelectric sensors are used to pick up acoustic emission waves that are produced when a material undergoes stress, loads, and deformation. These elastic energy waves can be measured and translated to voltage over time using data acquisition systems. In structural health monitoring applications, acoustic emissions is typically used to detect, locate, and characterize damage. Now, a common method in detecting damage is doing a manual crack detection. After conducting the tests on the specimens, the results look much more unorganized than these plots shown on the slide. These plots were produced with our device and are considered post-process data. After an engineer manually identifies what is considered noise and what is considered the specimen under stress, analysis can begin. Putting a specimen under a steady, either constant or increasing load, a continuous type waveform in the amplitude can be noticed in the data. When the load becomes too much and the specimen is ready to crack, it can be noted that the acoustic emission amplitude increases drastically. This observed increase in the AE amplitude coincided with the visually confirmed onset of cracking on the surface of the specimen. It can also be noted that there were some discrete increases in the AE amplitude prior to crack initiation. These discrete increases in the AE amplitude could serve as a crack precursors and therefore act as early signs of impending damage. If you look at this figure, the arrow draws right at the point of crack initiation, and you can see the spike happening from steady noise to crack.
As a proof of concept for our device, we chose to take the previously discussed manual crack detection paradigm and automate it. On the screen now, we can see the various methods used in the prognostics and diagnostics phases of our data analysis. Starting with normalization. Normalization is used to remap different features of incident data having variable ranges into one uniform range. For example, if two features, let's say amplitude and rise time, have ranges 0 to 1000 millivolts and 300 to 700 microseconds respectively, normalizing the data would bring both the features to have ranges close to 0 to 1. In our approach, we used min-max normalization to normalize historical compound tension test data. Next comes feature selection. In machine learning and statistics, feature selection is the process of selecting a subset of relevant features for use in model construction. In our approach, we used Pearson coefficient to drop features which were more than 90% correlated. These chosen features are also sent back to the fog device to filter out irrelevant features from live data. The chosen subset of data is then passed through a user-defined clustering algorithm. Cluster analysis or clustering is a task of grouping a set of objects in such a way that objects in the same group are more similar to each other than to those in other groups. In our approach, we used a Gaussian mixture model to cluster our data into two groups, signifying records that were received before crack initiation and records that were received after crack initiation. These labels are then used to train a user-defined classification model. In machine learning and statistics, classification is a supervised learning approach in which the computer program learns from the input data and then uses this learning to classify new observations. In our approach, we tried several different classifiers, each having a different performance score. We will dive a little deeper into this next. On this screen, we can see the different classification algorithms we tried, starting with support vector machines or SVMs. The objective of the support vector machine algorithm is to find a hyperplane in an n-dimensional space that distinctly classifies the data point into different classes. Using the clustering results from our Gaussian mixture model as labels, we trained our own SVM model. This model performed very well and achieved an average cross-validation score of 90.89%. Cross-validation is a technique for evaluating ML models by training several ML models on subsets of the available input data and evaluating them on the complementary subset of the data. Similarly, we trained a decision tree and a random forest classifier. Decision tree is one of the predictive modeling approaches used in statistics, data mining, and machine learning. Decision trees are constructed via an algorithmic approach that identifies ways to split a dataset based on different conditions. In our implementation, decision tree produced an average cross-validation score of 86.87%. Lastly, random forest, like its name implies, consists of a large number of individual decision trees that operates as an ensemble. Each individual tree in the random forest spits out a class prediction, and the class with the most votes become the model's prediction. In our implementation, random forest produced an average cross-validation score of 93.13%. Overall, we can see that the random forest algorithm performed the best, with the SVM model coming in at a close second. But since SVM models are more lightweight and agile than random forest models, we chose to load an SVM model into our fog device to perform an in-depth throughput analysis.
On the screen now, we can see the throughput results we've achieved using the previously mentioned SVM models being run in real time. An overall throughput of 44.4 megabytes per second was achieved. For this test, 1.53 gigabytes of data was already present on the PNP device. The PNP device was running two scripts. One script was parsing, filtering, and clustering the data, referred to as pre-processing. The other script was in charge of uploading the data to our MongoDB server, referred to as cloud upload. The pre-processing portion produced a throughput of 68.3 megabytes per second, and the cloud upload portion produced a throughput of 44.4 megabytes per second. The timers were used in both scripts to measure the amount of time taken to process the available data. The throughputs were then derived by dividing the total size of data by the amount of time taken. We went through 4 iterations of this process and took the mean of the throughput results to arrive at our final values. Since the overall throughput of the system is throttled by slowest pace, the final throughput was derived to be 44.4 megabytes per second. For context, similar tests performed on a sample of commercial acoustic emission data acquisition systems available at the lab produced a maximum throughput of 10 megabytes per second.
Now, for the enclosure design, on the left-hand side here, in A and B, you can see a 3D rendering of our case. Within it is the Jetson, battery, and Wi-Fi module, all 3D rendered in. In C and D, you can see the thermal imaging of the Jetson running near max capacity, which when deployed in the field, it will not be running anywhere near that. Next up, for the methods, the software used during this project was PyCharm, Visual Basic, Notepad++, the RMS 3D deformation analysis software, MongoDB database management system, as well as Fusion 360. The materials and their fabrication methods are the ABS plastic, which was used to 3D print the case, as well as the cold-rolled low-carbon steel, which we CNC'd out to make the testing specimens. Onward to the context and impact is the fact that with our intelligent maintenance, the amount of reactive maintenance will decrease considerably since the companies will have the current state of the structure in real time, and this real-time analysis will allow those companies to be more proactive with the maintenance that they have to do on the structures while minimizing the amount of cost and time spent for the engineers analyzing the structure as well as the needed maintenance before catastrophic failure. For our project management area, our total budget wound up as $4,241. Out of our $5,000, that leaves us still with $759, with device testing and the cloud components each being approximately $1,000. Looking back, at the end of the full term, we had the architecture of the system determined as well as the components for the system ordered. As the winter progressed, we had components come in one after another and started compiling them all into the device. Towards the end of the winter term, we started coding the system as well as the web application. Towards the end of the winter term, we designed the case and started 3D printing it. We wanted to start the proof of concept testing, the validation testing, and the final optimization of the system. However, due to the COVID-19 crisis, we were unable to access Drexel's labs, and thus unable to perform them. However, the final optimization of the system has been continued on using historical data.
With our device, we hope to alleviate all uncertainties associated with contemporary maintenance paradigms, all while giving users access to real-time information about their structure 24/7, 365.